Anyone? One or two? Any form of distributed application? Any form of application that involves more than one user? Right, I think we covered the room, right? So, success, what does that look like? Success is when you can actually satisfy every user that wants to use your system. And in some sense, that's really the problem we want to have. We want to have the problem of scale, we want to have lots of users, and we want to successfully satisfy the requests that they put in, right? But success is actually also a double-edged sword, because in many cases, the applications that we build, when they start getting successful, land up falling over because they're so popular. And scale is really both the friend we want at the party and the monster that we want to destroy at the same time. And over the years, we've had many ways of trying to battle this problem, right? So we've got rules of thumb, different platforms, people telling you should use this tool or that, this way of writing code, this, don't follow this pattern. This is kind of the evolved sort of knowledge that we've picked up over the last few decades of how to build scalable systems. And now, we are still having this problem. We still have the problem, so we haven't solved it. And I think there's a way of actually approaching the solution, approaching the scale problem a little differently. And that's kind of what we're going to be talking about over here. My name is John Azariah. I work for Microsoft as a software engineer in the Azure division.
I'm Sergey Bykov. I work at Microsoft as lead of the project.
Project Orleans, right? So we're here to talk about Orleans. Orleans has now been in the wild for some time now. It's an open source project and all of that. It's also fairly successful in the sense that Halo runs on it. And we land up having quite a bit of a scale issue solved over there. And we found that as we go forward, we see this very simplistic diagram that gives us an idea of what the kind of issues that we solve at different levels. So when you talk about single server type applications, we tend to write applications in a particular way. They tend to be simple to write, simple to read, simple to reason about, but they don't scale. And then as you go up, you take different approaches going higher and higher to different environments. So by the time we get to the point where we're dealing with situations like Halo, where you have to provide low latency services across the globe at very high rate of speed, the scale problems you're going to solve over there are quite different from the scale problems you have when you have a single server. So it also means that the approach that we're taking is going to be varied across the spectrum. Or so you'd think. We'd like to think that going forward, we should probably find a way to have the same way of thinking and allow some other system like the platform to do the heavy lifting for us. And in some sense, that's kind of where Orleans fits in.
So, not sure about it's just me or everybody else, but sometimes I find it more difficult to explain something simple than rather explain some complex concepts. I don't know if it's the engineering, the brain is wired this way, that's easy to explain complexity than to distill it down to something very basic. So I'll try it here. So there are different opinions of the object-oriented programming, right? But I think the truth is that probably 90% of software is done this way. So the essence of object-oriented, the right object-oriented approach is that you have encapsulation of entities in objects and encapsulate their state and their behavior. So they expose functionality through interfaces and they process incoming requests with method calls. So you hold the reference to an object and maybe you call some factory class, get the reference to the object, make a call, and if there is some exceptional case, you know to put try catch and handle it. I'm not going to get into argument with the functional people. I mean, this is the reality of how most people write code. This is all possible and very simple, very straightforward when you run as a single process, as a single machine, single server application, because you have access to memory. It's a shared memory space. We can have direct memory references, which underneath the covers is a pointer. So this nice model breaks down when we go beyond the machine. A single server, no matter how beefy machine you put, has limited capacity in terms of CPU, memory, throughput. So the moment we go into multiple machines, we don't have access to direct access to memory on another machine. We cannot have a reference to an object on a different server. We cannot as easily coordinate and decide what to do. So what we've been told and what we've been doing is switch to a stateless model. It's going to forget how we've been doing all these nice object references, method calls. Now we do it differently. So the request arrives to the server. It usually goes to storage to fetch data for whatever item the request is concerned with. It may be a user profile, it may be shopping cart, it may be inventory item, order, doesn't matter. We need to go and read the state because we cannot have it in memory on every server. So we read the state, and if it's a read request, just return it. Like, for example, give me user address. If it's a write request, if we need to apply a change, for example, update user address, then we try to write it to storage. Try to write because in reality, we're potentially competing with other requests coming to other servers that may be concerned with the same item. For example, if you're trying to update inventory on some popular inventory item, you may have requests being randomly distributed across multiple servers. They're all trying to update, say, numbers, inventory numbers on the same item. And that's not really the pleasant thing to deal with. So we lost all the benefits of the object-oriented programming. We learned this new stuff, and it's inefficient in addition to that, because I process a request, I just got this data from, say, SQL Server, which is an expensive operation, and I throw this data away, even though in the next second I may receive requests for the same item because it's popular. So it's very inefficient to go to storage every time. So if I wanted to explain Orleans in 5 or 6 lines of code, it's really about this. It's getting back the object-oriented view of the world. Because that's how our brain, I believe, works. We see entities, we see interactions, we have different levels of abstractions. So in Orleans, you get back interfaces and objects that we call grains that implement those interfaces. And you get back method calls. So an object, grain, can hold a reference to another object and make a call. And that just works. If there is an exception, so if there is some error situation, unexpected situation on the callee side, you get an exception. You can put try-catch around it, just like in the single server code. The difference is that this code that looks very similar to what we had before now transparently can run on a cluster of servers. So you can run it on a single machine as is, no problem. But if you add more machines, if you add more servers, they will automatically form a cluster. And these objects can live anywhere in the cluster. You don't have to really deal with that. You just program as if it's still a single memory space. But now it's scalable. And because these objects are isolated, they encapsulate their state, and we don't see any physical address here, we can easily scale out. We add more hardware, we linearly get higher throughput. So in fact, this model has even more benefits than the original model. In the original model, if you shut down your application, all your references are lost because of physical reference to memory. In this case, we have logical references that under the covers get resolved. So we can save these references to storage, read them a month later, and they will still work. So in fact, I would argue that this model is even more powerful than the traditional one. And there's this interesting conundrum when there's something is that simple, that our gut reaction as engineers is that if it's simple, it's probably too good to be true. And I've seen this reaction for years. When we started showing it work, the initial reaction was it's probably a toy. Because if it's something like you write a few lines of code and it scales and it works and it's performant, you're fooling me somewhere. That was kind of explicitly or implicitly stated response. But like John mentioned, we've proven that by running very demanding workloads, like anybody who knows about Orleans knows about Halo, because they were the first marquee customer. They run services for tens of millions of users and hundreds of thousands of requests per second they process. So it cannot be a toy if it runs that way at that scale. And we have properties like Skype or Azure or some services in Azure running it at a pretty good scale. So it's not a toy. So it is kind of something that takes time for engineers to believe that it's actually true because of its simplicity. But it's simple and it's very basic, but it enables a number of scenarios, a number of patterns on top of it. And that's what we're mostly going to be talking about, different patterns that emerged over the years. Because Orlean's been used in production for more than 5 years now. It's been available outside of Microsoft for about 3 years. It was open source 2 years ago. So what I noticed that once developers go over the hump of disbelief and see, okay, this actually works, they get the other, sometimes go to the other direction, and they're so enthusiastic they want to apply it everywhere. And sometimes I had to kind of curb their enthusiasm and say, well, you probably don't want to put this code onto your mobile device because we didn't care about power efficiency. That's not a good place. But the simplicity and ability to create many different patterns generates this enthusiasm. But what actually you get from it is you have to write less code. By some conservative estimates, we've seen it's like 3 times, in some cases 5 times. Some people claim 10 times less code. And it's simpler code because you get things like single-thread guarantees and non-reentrancy by default. So you write less and simpler code, so you get developer productivity. The same developer can produce a lot more functionality and focus on actual domain problems, not on the plumbing, on sending messages, on handling machine failures and things like that. And as I mentioned, it scales by default because of the model, because these objects can be isolated. There is message passing under the covers. So the model is simple. There is this complex machinery under the covers in Orlean's runtime that enables it, but the programming model is kind of scarily sometimes simple. So this is kind of the summary they already covered. So we open sourced the project 2 years ago, and it attracted an interesting set of people. So it's an interesting community of people all around the world. It's one of the probably friendliest and most welcoming community. That's what we're hearing, that these people are so awesome just to kind of spend time virtually and like chat. So they keep producing features and give feedback and fix bugs and do a lot of good stuff. But we never actually look at the numbers, so we never really cared or had time to look at the GitHub. And then, I don't know if you know this guy, Matt Warren, he, a few weeks ago, ran this analysis across all repos in .NET Foundation organization for the last 2 years. And then, to nice surprise to us, Orleans came up at the top as number 2 on issues, number 1 on pull request in terms of percentage of contribution by the community. So to me, it's a sign of very healthy community and then very good progress. And I think we strike a good balance there because there is constant investment from the corporate side, which is driven by internal priorities and our collaboration with Microsoft Research, and a steady stream of contributions, ideas, implementations, extensions from the community. So it creates this healthy balance of kind of on both sides. So now we'll actually switch to the patterns that we'll start.
Thanks. Okay. So as Sergey pointed out, the whole idea of the traditional way of looking at objects, back in CS 101 when they introduced objects to you and you started talking about encapsulation, abstraction, the ability to hide data and provide controlled access to modify it, and so on and so forth, that benefit kind of went away when we went to the stateless world. We're trying to reclaim it and bring it back. So what exactly are we trying to do? If you look at a single object, there are 3 kind of key pieces in the object, 3 attributes of the object, if you want, aspects of the object that you want to think about. Of course, there's the initial piece, which is the encapsulation part of it, right? We hide data, and we allow controlled access to it. But the objects are basically centered around some form of data. So you can store data in there. There's an object piece there. And then, of course, there's operations on that data, and the object allows you to sort of make sure that all the related operations on the data are present in the same place. And so then there's communication between objects. So objects A can talk to object B by virtue of a method call. And that's So if you look at the structure of an object, there are three facets to it. There's the state facet, the compute facet, and the communication facet. Taking Orleans and applying the object-oriented paradigm, you'll find that there are several applications, as Sergey pointed out, that have been developed. And one of the things we notice when we look at the kind of applications that are developed is that there are patterns that emerge from each of the different facets. So there are data-centric patterns that you can apply. There's compute-centric patterns that you can apply. And there's a class of patterns that come from the fact that objects can communicate with each other. So I'll talk about the state-centric ones first. The first and most basic thing that you can do with a piece of data is to store it. And Orleans allows you to basically encapsulate a piece of data in a grain, give it an address, a way of identifying it persistently over time, and store it somewhere. This is quite useful. For example, if you want to write Facebook and you want to have a profile per user, that profile is kind of an object. It has an address which is some form of the user's name, and you want to be able to store it and retrieve it. So a common pattern would be to create an object for that profile and effectively use the Orleans grain to store it. So one of the things we've done is we've been able to come up with a commonly used set of patterns and pieces of code that you can just download as a library, and you'll get that for free. At this point, because we haven't really talked about Orleans in some detail, how it actually works, I'm going to talk a little bit about what it means to store an object in Orleans, right? So if you think about a persistent object, you have some amount of working space, memory space, and then you have a whole bunch of disk space somewhere, database or Azure storage or whatever it is, some persistent storage and some working memory. So the way Orleans works is you never new up anything. You ask a factory to give you a reference to this grain, which could basically live somewhere else, but you get a reference to it locally. And what that means is that grains effectively are eternal. They always exist, because if the system doesn't have a grain with that address already, it'll create it when you ask for it. And it'll store it where you tell it to store it. So the life cycle of a grain kind of looks like this. It's either persisted or it's non-existent. When you ask for it, the system will activate it and give you an active version of it. So at the point when the grain is active, there's a machine somewhere in the cluster that has this thing in memory with an address on it that you can actually talk to it with. And so when you call user.do something, what actually is happening is a call is being made to that machine with the message being sent to go and do something with those arguments. And then you await on that and you get back a response. So you have persisted grains that are effectively in cold storage, and you can have no limit to them. So it's not like a toy database or anything like that. You can literally have terabytes of grains lying around. You activate the ones you need, and the system takes care of bringing it into being and giving you a reference to it. It becomes active in memory, and when you stop using it for some time, and the system decides that it no longer needs to keep the grain in memory, it'll deactivate it and put it back into storage for you. So in some sense, it's like virtual memory, but virtual memory across a cluster. An analogy might be, you don't really care which stick of RAM in your machine has the memory that a single object lives in. You don't care about that. There's something that abstracts that away. At a higher level, Orleans abstracts away which machine in the cluster has this object that you're talking to. You just deal with it as if it was always there, right? So a pattern like that, fairly straightforward to use. So let's assume that we were writing some form of e-commerce thing, and this is the object I want to store, right? I create one of these things and make it serializable, and then we have this cached item grain, cached item grain interfaces that are already available that you can just leverage. And what that they give you two methods on it. One is to get an item, and the other one is to set it. And effectively, this is how you'd use it. Can everyone see this code? Is it too small? Is it all right? I'll give you an idea. The first 4 lines, the big block, is basically just creating the grain state itself. That's the instance of the object I want to store, the data that I want to store. And I try to get the grain and then set it, and I'm done. And when I want to read it, I just ask for it by ID, and it's there. So effectively, this way of doing it means that I don't have to write any Orleansness behind any of the stuff. Even the interaction with the Orleans system is abstracted away by the pattern, which is kind of useful. This pattern is so popular that it more or less becomes something that you can use right out of the library itself. Another thing that might be useful is to keep track of a set of grains. So in the case of an e-commerce thing, say you wanted to get, you're running a shoe shop, and you've got different models. So you have a grain associated with each model, and it keeps track of how many of these you have. But then you also want to keep track of all the shoes that belong to children, or all the shoes that are for women, and all the shoes that are for men. And in some sense, it's a registry of grains. And when you want to keep track of a bunch of items that are of the same type, you can use the registry pattern. Again, the code I'm showing you here is actually the stuff in the library. There's already one there. You can just call it a registry grain and use it effectively the same way. If you look at what's happening over here, the grain that we first start with is a standard, it's an object storage grain. And that one is being registered with something else. So effectively, the state of the second grain is actually the list of grains that it needs to keep track of. And it doesn't mean that you have to only interact with the registered grains through the registry grain. You can actually interact directly with the grain itself, which is kind of useful. If you think about the ORMs that you've dealt with in the past, when you get back a set of things from the database, you can't really interact with the individual objects themselves and expect them to persist or have a life cycle of their own. You effectively get something as a result of a query that is equivalent to the registry grain, but additionally, every row that you would have gotten back is equivalent to a grain that lives by itself and has its own way of managing. So you can talk to the grain independently of the registry. Both these patterns together allow you to set up groups of things that you want to keep track of. And one of the places where that becomes very, very useful is in a caching layer. So having a system like memcached allows you to keep a bunch of cached items in memory, right? In many cases, we can do similar things with Orleans. And in fact, there's a whole pattern of a smart cache that Sergey is going to talk about.
So first, why do we need caching? So the need for caching comes from the same challenge I talked about a few minutes ago. Because we're stateless and we go to storage, storage has a limit in capacity. And going there to read, when you have a lot of read requests, going to storage every time is inefficient. When you have high scale, your storage cannot keep up, or it's very expensive. So of course we put a cache layer like memcached or Redis in front, so that we read and put data in cache, and then we leverage data that's already in memory. It all sounds nice, except for now we need to talk to two storage systems with very different semantics and very different characteristics. Whenever there is a write, we need to write to cold storage, like a SQL database or key value store. And we also need to either update or invalidate cache, because we just changed the value. And there's this famous saying that there are two hardest problems in distributed systems. It's naming things and cache invalidation. This is not an easy thing to do, to coordinate that you don't return outdated data. But also you need to run a separate layer. So you need to deploy a cluster of memcached or Redis or use separate service. And, which may not be as obvious, you move data between machines. So your data is in memory, which is great, but then you send it over the network to another set of machines for each operation. So it's much better than going to storage, but it's still sending data. over the wire. So the Lynch approach is very simple. There's really no approach, because by itself, grains are natural cache. When grain gets activated, its state gets loaded from storage, and it's just naturally cached in memory. There is no separate statement or effort or line of code to write. It's already cached there. So we eliminate the need for extra layer, an extra tier right away. But we also get more benefits. Unlike in, say, memcached with key value based cache, where you just write some bytes of data or strings, here we have semantic operations. So when request arrives to update user address, it may arrive as a move with new address, and that can be processed that way. Or there's a marriage operation when it includes change in the last name of the person. So all these operations can be expressed in a natural way instead of just saying, override whatever you have there with its bytes of data or the string. So that's good to have semantic operations. But also, now we're shipping functions. So whenever request arrives, we don't move data. We don't send data over the wire. Data sits in the memory in the machine, and the function, the request arrives to that piece of data, that piece of state. And actually, this is the most popular pattern altogether, I think, over all the applications we've seen. So there are different variations. The simplest is read-only. So when we need to serve video files, any kind of items, catalog items or descriptions, data that kind of never changes, it's immutable. We just cache it in memory. It's very easy. So grain gets activated, loaded state once, so there's only one round trip to storage, and after that you can serve this data as long as you want until that item becomes cold, and if it's not used for an extended period of time, it doesn't make sense to keep it in memory, we can remove it from memory. And next time there is a request for it, we'll activate it again and do another round trip to storage. The most popular one is write through. So in addition to reads, you may receive writes. And because writes go through the grain, they don't go directly to storage, and doesn't go to two places like storage and cache. They go to this grain, which has data in memory, and then grain writes it to storage. You have this very important property that your writes are serialized. They never compete with each other. You eliminate this situation when two servers can write to a single line in storage, like in table. And again, you have semantic operations unlike with normal writes. And you would think that serializing writes may not be a big deal because you have protection, you have E-tag support in most modern storage systems. But in fact, that may be a very significant performance boost. A couple of years ago, maybe 3 years ago, some people in Skype created a service which was probably like 100 lines, maybe 200 lines of code. It was a very simple, very trivial grain class that all it did was receive telemetry, which was routed to a specific identity. So all writes to a single line in storage, they all were going through a single grain, which eliminated all write conflicts. Very simple application. But because of that, because of elimination of storage conflicts, write conflicts, they received 4 times throughput improvements. Or if you flip it around, they reduce their cost by 4 times, by just merely eliminating a contention on storage. So even simpler patterns can pay back pretty well. If you don't have to write necessarily every item reliably to storage, for example, you are writing performance information, like performance counters, and you can afford to lose some of the readings, like once in the blue moon, or you're logging through it. Then you can batch your writes. In this case, you can write behind. You can receive requests, but don't write them immediately to storage. You can accumulate either a number of them or for a period of time and then write from a grain. It's very easy to implement because there is support for timers. You can set timer fire every minute or count number of updates or a combination of both. And the code is simple because you don't do anything special. So there is, if you use declarative persistence, you have a state object. You can declare separate interfaces for reader and writer. So you can give read interface or a grain reference that implements the read interface to the reader and a different one to writer, or you can combine them and give it to some other entity in the system. So you can do all the same like separation of concerns, and this is kind of trivial example, you get a reference for a particular interface, reader or writer, and then you do either operation defined on the interface. And when you implement it, it's that simple, because you have your state object, and then you either update it or return it. And when you update, you just call this base class method to write state to storage, and there's persistence provider, kind of plug-in system there. So you can do that. This is the built-in default operation with declarative persistence, but you can write any code you like. What's important here from, sorry. From a performance perspective, it's important to partition your state.
Yeah, I think I'll take over. So, yeah, so basically, if you have reasonable persistence, and you can pretty much just use this out of the box. And I'll move on to the event sourcing one, because this is the one that seems to be the one that causes a lot of confusion with people. And it's one of the things. At the moment, persistence is you write whatever you want to through the write state async. So grain is associated with the class that is the kind of data that it stores, and you can actually use that to write. Now, Sergey mentioned semantic operations, which is actually just a, why is this thing? Oh. Yeah. Sergey mentioned semantic operations, which is kind of the same as sending an event in order to declare what you want to do, rather than mutating something and saying save it, right? So the concept, for example, of updating somebody's home address can be done using a semantic operation saying update the address, which then becomes a kind of event that you can log on the side saying, I updated the address with this. Now, by doing that, you get a couple of interesting benefits. You, for example, keep track of all of the things that mutate the object in an immutable store. So you have, or an append-only store. So you have a list of all the things that caused the object to become what it was, which is very different from a traditional relational store where you call update on something, and because you're updating that something, you lose two pieces of information immediately and you gain a problem. The two pieces of information you lose are, why did this thing change, right? What caused this change to happen? Because all you're saving is the fact that it changed. And the context in which the changes happened, like so as changes apply and accumulate, you've lost the history of the things that have caused the change to take place. Additionally, because you are mutating an existing object, you have welcomed in a very unwelcome guest, which is the issue of concurrency. You now have to do things like do optimistic concurrency or some form of strategy to make sure two people aren't overwriting each other's changes, right? The third thing, so one way to solve that problem is to basically keep track of the intent of the change rather than the change itself. And we can do that by storing that in a grain too. So rather than just, so when we have semantic operations taking place, we will store the sequence of the operations that took place, apply those operations to keep track of an aggregate, which is kind of the updated version, if you want to think of it that way. But at any point in time, we could throw away the updated version and replay all the events to get to this state again. So the important piece is actually the sequence of events. And you can then talk about things like eventual consistency. Because you don't have a concurrency problem. There is no, even if two people try to make changes at the same time, they will get serialized into a log, and you'll find that somebody changed the home address and somebody changed their phone number, and they didn't clobber each other's changes. They just get applied one on top of the other. So by doing this, you can vastly improve the architecture, the scalable architecture of your application itself, because you're not now bound to some form of two-phase commit across a distributed system or anything of the sort. You can actually just keep track of history and just run with that. So with that model, we actually have a pattern that actually keeps track of timestamped values, and all you have to do is provide the semantic set of operations that you can apply to the service. So the T event over there is effectively equivalent to the set of operations that you have, such as, change address or change phone number or change shipping address or whatever it is that you want to do. And then this object, the event source grain, will automatically keep track of the history of the events as they apply. And then you can provide, so let's give you an example before. Let's say that I have a bank account grain up there. So that's an iBank account grain. I can show the account state, which is the current balance in the account, and then I'm going to call credit amount on it. But what happens beneath the covers on credit amount is that gets converted into a message, an object that can be stored. So rather than just update the value in a standard object-oriented way, we create an object called credit amount with that value, store that, and then apply that object to the aggregate. Now, what will end up happening is that the balance will still get updated, but you've kept track of the fact that you've now credited the amount of $100 or whatever. So all of this code, by the way, is live code. It's there on GitHub. If you get it down and play with it, and you run it, you'll actually see the sequence of it going up to $100, and then $50, and then $150, because you credited, debited, and credited again. The value will continue to be $150 just as you expect it to be, but I will also be able to tell you, first you credited me $100, then debited $50, and then credited another $50 on top of that. So I'm sorry, so it'll go back to being $100. Sorry, my maths is not that great. Anyway, right. So the other key thing is to realize in this whole thing is that this has all the hard work already done for you. So the library pattern that has this thing already has event sourcing built in. So all you have to do is provide T event and the other type arguments, and you're done. You can actually just go ahead and use it. Right, aggregates. So as we start looking at various patterns, one of the things that you'll realize is that you can form bigger patterns from littler ones, and they become patterns too. So when we talk about, say, for example, object stores, what's the first question you're going to ask me? Let me guess. How do I keep track of a total? Right? So you're giving me all of this stuff about the eventual consistency and all of that. How do I get a report? How do I get a set? How do I get a total of something? And one way of doing that is to keep track of the things that is going to affect the aggregate, and then keep a registry of your total always in place. So an aggregate basically allows you to bring events from a whole, so let's say you have a bunch of bank accounts. You keep a registry, will keep you a bunch of bank accounts, and an aggregate can listen to the events from each of those grains so that you can now keep a set of events that come from all of the grains into the one place. So if you think about why a total is formed from a data set, it's effectively what you're doing. You're able to reduce across a whole bunch of grains into the one thing, and you provide the function that does the reducing in the aggregate grain. And then in a very general way, you've solved the idea of being able to run a query. But even that terminology is wrong. We don't run a query anymore because running the query assumes that the data is basically useless the moment you finish querying. Something may have changed it. This one is actually going to aggregate and keep a query for you. It's a standing query. Every time an event takes place, you can actually collect the event and then apply the event, the set of events to get you the result that you want. So you can basically ask for an aggregate on demand, in which case you don't actually let the event do anything other than say, hey, I happened, and then go away. And then when somebody's interested in the total, that's when you go and play all the events together to get the total that you want, and then you can get it back. Or you can do a timer-based thing. I used to, in a past life, work for an accounting company. End of day is always useful, because end of day reports is what you kind of need. So I can quite easily keep track of all the transactions that took place during the day, and at the end of the day, automatically compute a transaction. Now, if you think about that, that actually makes a lot of sense, because everything is immutable, because the events, once they happen, never change. So the reports that happen, the aggregate as of a given time is also immutable. And so you can run it very efficiently and never have to pay the cost of running the same query twice. And then, of course, you can have any kind of strategy that you want to actually bring the aggregation to pieces. So here's where you do the get aggregate value, and effectively, you can see that the functions at the bottom tell you how to deal with a credit and a debit. And they're basically just lambdas that allow you to plug in whatever functionality that you want. But all the plumbing associated with keeping the grains in a single registry, getting the events to be propagated to the aggregate grain, and then applying all the events at the time when you need them, all of that's done for you automatically. So bank account aggregate balance will now keep track of a whole bunch of bank accounts and be able to apply the events as they come through the pipeline, right? So let's see. Right. This is actually an example of how this would be used. So this is actually the internal structure of what the bank account aggregate balance would be, because you have to provide me the fact that there is a credit and a debit, and what does credit and debit mean. If you can provide that information from here, then I can let you write code like this. As in, I'm going to create a bunch of accounts, right? That's the account grains. I'm going to register them all in the aggregate grain, and then take the first 10 accounts and credit $100 to each of them. And when I do that, I expect that the aggregate effectively should be 10 times 100. So if I were running a bank, it means 10 accounts had $100 credit to them. I jolly well have $1,000 somewhere. I should. And then you can take it and add another 100, and you'll get back at 200 at the end of it. And effectively, the programming model, if you notice, is still very object-oriented. It's just that we've started composing more and more complex objects together to give us quite useful functionality from that point of view. It should be said that you can then go to the aggregate grain and then look at what caused the value to be $200. And it can report to you that it is that way because these accounts had credits of $100 each, and then these accounts had a credit of $100 each over a period of time. And you'll get a timestamped list of all of the things that you can work with. So it also means that you can build up totals out of band. You can delay building the total until the end of day, or whatever it is. It all depends on your computational strategy. The other cool thing about event sourcing, which works out after your system has been in place for some time, is that you can build aggregates on data that you can build aggregates on old data that weren't there when the data was being formed. So let's say that I'm interested in new piece of information. When was the credit? When do people most actively credit money? I could create a new aggregate that actually filtered everything and assigned time of day on them, and then run it on all the historical data and get back the information. I haven't lost anything from that point of view. And so this event sourcing approach is fully supported in Orleans, and it's as native as you can expect any other form of persistence to be. If you think about that, we've actually kind of created a full-blown object store, right? We've stored individual objects and got them back. We've kept track of groups of objects. We were able to get standing queries set up, and we were able to do event-based semantic operation tracking, right? And in many cases, that's pretty much what you use your database for. So if you squint a little, you can potentially get by quite a far way and get rid of your separate relational store by keeping a stateful set of objects in memory and be able to handle everything that you want. In fact, in the roadmap, as Sergey will point out in the future, I'll steal his thunder now, the people in Microsoft Research that are actually talking about putting transactions in play for this. So now when we want to do updates and sending information across, it's not just, let's just make one thing happen. We can actually give you a guarantee that all of these will happen or none will happen at the same time. At that point, we've actually converted this thing into a kind of object database. Now, there's a whole bunch of baggage associated with the phrase, so let's not go there. The reality is that in more than one occasion, it is entirely possible to write a full-blown, scalable web application without using a database at all, just using the Orleans middle tier to keep track of just the data side of things. Now, I think we've done a little bit about data. I'm happy to take questions, but we also have time for questions later. I think we're going to talk about the communication side. Now, remember we talked about the three different aspects of objects. The data storage piece is what we just covered. There are some patterns around communication that Sergey is going to get into. But if anyone has a question, I'm happy to answer it now.
I'm not sure if I've understood the model correctly, but by the sounds of it, you've got lots of objects living on lots of different physical machines. How do you go? It seems to me that you've just multiplied the risk of one of the machines. It seems to me that you've multiplied the risk of a machine dying, and then all of a sudden you've lost some amounts of grains. And how does the system cope with that? How does a KISS system cope with failure?
Sure. Let me repeat the question, and I think can you handle it? Yeah. So the question asked was, now that you've actually taken your objects and put them on multiple machines, how do you deal with the fact that one of them may fail and take some of the grains with you?
Well, the simple answer is grains never fail because they're logical. They have their state persisted. So if one machine blew up, the Orleans runtime will recognize it, remove that machine from the cluster, and reactivate grains that are needed on other machines and reload their state there. And because you're completely location transparent, you don't really care if those grains moved.
So you'll just see a slightly higher latency whenever you're talking to those particular grains that have now, or were living in memory on a machine that has now died.
Well, they'll be in memory on another machine, and latency between machines is under a millisecond, so you will not see any latency. Just think of it as the cluster reconfigured, and it keeps going.
Okay, thanks.
1 more.
Can you version your events? Let's say you revision your events, and then you would like to actually reapply them to your grains. Can you do that?
Sure. I mean, it's just version grain is just an extended version of a standard event, right? So you can potentially extend these patterns however you want. But remember that none of this stuff, if we are talking about building patterns to make stuff useful, the primitives that we're talking about are effectively object-oriented programming. So we're coming back to the same thing. If you can do it with an object somewhere, we can do it with Orleans. And usually with not much more difficulty. So the versioning is exactly the same story. So
you can rewrite the history basically on the grain.
If you want to, yeah, you can. Sorry, carry on.
Thank you.
Are we running out of time?
Yeah. So the next pattern is the object graph. So it's kind of a pattern and not at the same time. When people hear about graphs, they think about graph databases immediately, or about Facebook with a graph of whatever billion plus users. But in reality, a lot of things are like graphs. So like in the gaming example, you have these players that form short-term relations during the game session when they participate in the same game, and then when the game ends, those relations end. But they also have long-term relations if they're part of a clan or of friends, so you can communicate that way as well. For example, they chat with each other, send messages, invites to each other. And so for that, in Orleans, you don't even need a pattern, because you can have these references, you can hold them, you can store them, which you cannot do with objects, and have just list of your friends saved in the database, and anytime you need to send a message, you just make a call. If that grain is not in memory, it will be activated. But if you look at this picture, it's intentionally the same, but instead of gaming, there is IoT scenario here. So it's either devices and rooms and control objects or something else. For example, a popular pattern is with tracking vehicles, you divide your geographic area into tiles. So as the vehicle moves and reports its position, or a cell phone reports its position, this vehicle grain or avatar that gets updated with the position and can re-register itself with different tiles as it moves on. So when you need to send a notification to all the grains within all vehicles in a particular tile, you just need to talk to the tile grain, like with aggregate pattern or with the registry pattern, and say, hey, update all these vehicles. In the reverse is also possible. You can analyze data and query it across these geographical tiles for traffic optimizations, things like that. But the programming model is exactly the same. So you use references as the dynamic relations that you establish for short-term or long-term. That's what it's about. So we'll go through streaming quickly. So we introduced Orleans streaming about 2 years ago, and streaming is a very overloaded term, including video streams and data streams and Kafka. In Orleans, what stream means is the logical abstraction of a named entity. So it's just like grains have identity, unique identity. Streams, Orleans streams have identities. And so long as you know the identity of a stream, you can always either produce a message to the stream or subscribe to consume messages from the stream. So they kind of always exist just like grains at the logical level. But physically, they're multiplexed over some physical queues usually. For example, if you have hundreds of millions of users with individual per-user streams, you will have a hard time finding a queuing solution that would support hundreds of millions of individual queues. But they get automatically, these logical streams multiplex over physical queues, so you may multiplex this 300 million users over, say, 1,000 queues, because your events are infrequent per user, and it's a matter of event frequency. And then these logical streams, they can easily be mapped to grains that are interested in processing them. And the mapping can be done either through explicit subscription, say, I'm interested in events on the stream with this ID, or even implicitly. Like in this example, by merely putting an attribute implicit subscription, I'm declaring that grains of that class whose identity matches to the stream identity within the namespace device alerts, they should automatically receive events of those streams. So by just putting that, you eliminate the need and just need to install a handler, a pointer to a method to handle the message. And those stream messages are delivered through the same exact mechanism, just like method invocations. So in terms of writing code and implementing grain that handles messages delivered through one or more streams, it's the same as processing a method call. There are various scenarios that this enables. One that I wanted to point out, like cheat detection. So in gaming, cheaters can be very poisonous. If you find somebody who misbehaves or find a way to exploit the system, you want to shut them down as soon as possible, ban temporarily or forever. So you need to automatically detect that somebody is doing that. For example, if somebody exited the multiplayer game more than 5 times over the course of 10 minutes, that's a sign of a cheating, one pattern. But interestingly enough, another customer of Orleans was using the same pattern for detecting credit card fraud transactions, because you receive events and you look for patterns. If somebody did a couple of gas station transactions and then went to a shoe store, that's a suspicious pattern, at least in the US, that they block the card immediately. So by subscribing to events and putting this logic and very simple pattern matching, you can do it. The most advanced pattern is a state machine pattern. And actually, we're not going to talk about it today in this talk. But later today, John will be talking about just that pattern alone and the tooling he created for it. So you can define the state machine within the grain with a simple declarative definition of the state machine. So it's going to be a very interesting talk, I promise you. We didn't talk much about the cross-cutting benefits of Orleans, but it's worth mentioning them because the questions of what happens in case of a failure naturally emerge. Orleans handles all of that. So it handles the cluster state. It understands if machines go down, if network partition happens. There is physical sending of messages over the network to ping and check that machines are available and messages are going through. So Orleans runtime by itself automatically detects failures, like if you have a cable failure, and will automatically readjust so that grains will get recreated on the machines that are still part of the cluster. One thing that is not immediately obvious that the fact that Orleans deactivate grains that are no longer used, actually that gives you complete automatic resource management. So you just ask, give me a reference to a grain with this ID, give me a reference to a grain with this ID, and they get activated automatically. But you never need to do anything to clean it up because they get collected, garbage collected effectively at a specified time. You can say, keep them in memory for 2 hours or for 5 minutes. You can specify it by type. You can even programmatically tell. So that eliminates a lot of the concerns of resource management and makes it very efficient. Quickly, what is on the horizon? We published end of the year a tech preview of .NET Core compatible version. There's a lot of interest running Orleans on Linux and Docker and things like that. We recently enabled this very interesting feature of support for geo-distributed multi-cluster, where in addition to being able to run a single cluster of servers like today, you can also run multiple clusters that are logically combined into a geo-distributed cluster. They're aware of each other. So you keep the same programming model of the single grain in the cluster, but now it can be anywhere within this sort of constellation of clusters. So you can deploy to multiple data centers for availability or for latency. So you can have grains automatically activated near the user where the requests are from the user coming in. So the Australian user doesn't need to talk to data center in US, can talk to data center in Australia. But if that same user happened to travel to NDC in London, his grain, if he launches an application, will be activated in the nearest data center where it would automatically be routed to. We also continue collaborating with MSR. Actually, the project at Orleans originated in Microsoft Research. Now it's in the product group for a couple of years, but we continue to work on other interesting extensions, like, for example, support for full asset transactions that John mentioned. Indices, so you could query and say, find me all the users with such and such characteristics or in this geographic code, and some other interesting stuff. So we have links to the resources here, the code base, which is obviously on GitHub. We recently started the blog. We have this chat in Gitter where the community lives, and it's very nice to kind of look what people are talking about and participate. We have a staging repo, Orleans contrib, of things that are not ready yet, but kind of being incubated. And as John mentioned, code for this talk is available. So thank you very much. If you have any questions, just come to us.
Can you just take the slide one back? Sorry, so I can...
Yeah.
Oh, sure.
Any questions? We've hit the time limit on the nose. So. Yes.
Streaming in Orleans, just to compare. Streaming in Orleans, do I understand correctly that if you compare with Akka streams, that you can define your process workflow and then you can materialize it in a similar way without explicitly getting your grain, so it will be created for you, or is it something else?
It is kind of decoupled, or allows it to be decoupled. Like, for example, your ingestion layer that ingests data into queues, like in Event Hub or Azure queues, may have nothing to do with the consumption cluster. It doesn't even have to be part of the cluster. So you have this, because of the queues, you have separation of concerns. On the processing side, you just define declaratively or programmatically what streams, logical streams, your grains should be subscribed to. And whatever data comes in, either from grains or from Orleans or from outside, it will get processed.
And these declarative definitions, they don't need to deal with grains explicitly. They are sort of on a function level, or you need to do some grain processing.
They're done on the grain, the class definition layer, if you use implicit subscription. So you declare this class needs to be subscribed to such and such stream namespaces. Mm-hmm. So you can do that. But you can also be very explicit.
Thank you.
I think we should take it offline now. We're done.
Yeah, just come to us, because...
Come talk to us. We're very available. Also, please come to the 540 talk, because it's really all about the whole state machine problem, and we'll talk about how to write safe, scalable actors that embody state machines in the cloud. Thank you.
Yeah.